Hello, here we are with our next lesson, Unit 1, Lesson 16. This will be the last lesson that I teach from this unit. Then we will prepare for our unit test. Today what we're going to do is continue talking about what proves that triangles have an interior angle sum of 180 degrees. So our goal by the end is to see why the angles of the triangle add up to 180 degrees, and your target or your goal is to be able to explain using pictures why the sum of the angles in any triangle is 180 degrees. As we work on this, I want you to be very thoughtful about the processes that we go through and recognize the use of rigid transformation in everything that we do. To get started, let's go ahead and talk about some relationships here to understand how structures of math are built. First part of this, 62 minus 28 is equal to 60 minus 30. Is this a true statement or a false statement? Something that we need to work to achieve in math is that we understand that as we make a claim, we have to have evidence. Right now, the claim is that this equation here, this expression, 62 minus 28, has the exact same value as 60 minus 30. Well, 60 minus 30 is something that's fairly easy for me to calculate in my head. I know that that is 30. The question is then, is 62 minus 28 also 30? So we're wondering if that's truth. I know that if I take 62 and I subtract 20 from it, I end up with 40. But then I take the 8 from the 2, it's a little bit of a different value, so I actually need to be regrouping here. And I can find out, you can use the standard algorithm. 62 minus 28, 8 from 2, regroup your 5, and we find out that this statement actually claims that 34 is equal to 30. We know that to be a false statement, not equal, so we would call this one false. We would work in a similar manner here to decide what is happening on this side. The expression on the left, 3 times negative 8, will be negative 24. Negative 2 times negative 8 is a negative, 2 times negative 8 is negative 16. Minus 8, negative 16, and we're reducing further or subtracting more, meaning that as I subtract, I'm going from negative 16, I'm going to subtract more, negative 17, negative 18, and so forth, to actually end up with negative 24, so this statement is true. The final one, 16 divided by negative 2 plus 24 divided by negative 2 equals 40 divided by negative 2. Let's go ahead and simplify each of these fractions to make this negative 8 plus negative 12 equals negative 20. Well, I know that 8 and 12 is 20, and when I have a negative plus another negative, I'm just increasing the values of those negatives, making this negative 20 is equal to negative 20. So the third statement is also true. All right, as we head on, the digital version of this activity is right here. Today we're going to look at what happens when we apply a rigid transformations to being able to prove that the interior angle sum of a triangle is 180 degrees. Tracing paper will be our tool for this activity. I'm actually going to try a piece of transparency. If you have a piece of transparency and just a dry erase marker, that will be something that we can use. We're going to explain the structure of the measurements of those interior angles and how adding them together is going to equal 180 degrees. So following our directions here on the bottom, we are to rotate triangle ABC 180 degrees around the midpoint of side AC. As we look at side AC, we see a length that is not a vertical or horizontal length, and so we have to figure out how can we cut that length in half. As we go from A to C, we drop down 2 units, and we go to the right 4 units. Half of that would be dropping down 1 and to the right 2 to make this our midpoint right here. We're going to call that one D as they instructed us. And let's go ahead and make our rotation of 180 degrees. Some of the things that we can remember about rotating 180 degrees around a midpoint is that our segment AC, which is part of that or where the midpoint is located, will actually just change to where A and C do not actually move off of the line, but they just end up in the same place. So rotation of 180 degrees around point D, that would tell us that point A and point C basically just switched places. And we can see that the relationship of where point D is, or vertex D in this triangle, is in the same relative location as it is on the other side, just 180 degrees away. And so we'll go ahead and mark that point. This one is point E. Oh, excuse me. I messed up earlier. This midpoint is not D. That was what we were supposed to name point B after the rotation. So we're going to call this one midpoint M. We'll go ahead and draw our triangle. Okay. Next, we are going to rotate triangle ABC 180 degrees around the midpoint of the side AB. Again, the same piece that we're looking at. This time I'm going to read my directions better. Label the new vertex as E. Oh my goodness, I still called that one B. Let's go with D here, as I was told to do. Midpoint right over here. We'll call that one in midpoint N. And then go ahead and rotate our figure. Now this time, instead of A and C just switching places, A and B will be the ones that switch places, because the center N is right on the line. So we know that a rotation of 180 degrees around that point keeps that point there and just switches the other two. And we have this figure that should look a lot like one that we've seen in the past. Make sure I label this correctly. A few lessons ago, we saw a very similar figure that was a few triangles. And what we found is that there's some commonalities between the three triangles, very common things that we're going to review again at this point. So when we look at our angles, it says look at angles E, A, B, B, A, C, and C, A, D. I want you to notice on here that there's something common about each of these three angles. The vertex, or the middle point of each of these angles, is point A. It says without measuring, write what you think is the sum of the measures of these angles. Explain or show your reasoning. I hope that what you've come up with is something related to the 180 degree, or the straight angle theorem, where we have a straight line here, straight angle that passes through point A, meaning that the added measure of these three angles right here will equal 180 degrees because of a straight angle. So we're going to need to make sure we tell it the three angles together make a straight angle. Oops. Now if we take the measure of angle EAB, or if the measure of angle EAB is equal to the measures, oh my goodness, I need to read better, is the measure of angle EAB equal to the measures of any angle in triangle ABC? If so, which one and how do you know? As I look at this and I look at angle EAB, we know that this triangle was made by rotating the original figure. Therefore, angle EAB would be the same thing as angle ABC, because we used rigid transformation You can see that here in our picture, since I know that this triangle right here came from this triangle right here. I see that when I keep my drawing over top of it, or my image over top of it, I can see the overlap of angle EAB is the same thing as angle CBA or ABC, whichever one you want to call it. The reasoning for that being true is because of a rotation of 180 degrees, or a rigid motion that preserved the angle measure. So is the measure of angle EAB equal to the measure of any angle in triangle ABC? If so, which one? How do you know? Well, we would say angle EAB is equal to, I should put an M here, that M means measure of. Angle EAB is equal to the measure of angle ABC, because of the rotation that we did right here. Rotation of 180 degrees around midpoint of side AB. Because of a rotation of 180 degrees around midpoint of side AB. Angle EAB is the image of angle ABC. So since that rotation happened, angle EAB was created by the same relationship as angle ABC. Likewise, if we look into the other triangle here, we're asking about what is the measure of angle CAD, asking is there any angle that is equal to any measure here in this triangle. And again, we can use the same definition, that because of the rotation of 180 degrees around side, in this case around side AC, we know that angle ACB, or this angle right here, is going to be equal to angle CAD. Oh my goodness. Yes, CAD. So we can just use basically the same exact wording here, except we would say the measure of angle CAD is equal to the measure of angle, and let's look back at it. CAD was angle ACB. And I would say the same wording from down here, because of a rotation of 180 degrees around midpoint of side, in this case side AC, angle CAD is the image of angle ACB. So if we take a look at those three angles, what we're saying is what is the sum of the measures of angle ABC, BAC, and ACB. They throw us off just a little bit, and they talk about what are the measures of each of these vertices. So the measures of the angles here are talking about angle ABC, angle BAC. So we're asking what are the measures of this angle here, and this angle here. Well, if we review what we just did, we rotated this angle and took an image of it right here. And then we rotated this angle 180 degrees to make an image right here. Therefore, what we can see is that through rigid transformation, these three angles are the same three angles that we see up above, meaning that the interior angles of this triangle ABC added together must equal 180 degrees. All right, let's go ahead and put this into practice. So every triangle in the world, no matter what triangle we have out there in the world, we can apply the same principle. Here we have triangle ABC, where lines D, E are as parallel to line AC. When the question is asked, what is the measure of angle DBA? So I want to know what is the measure of this angle plus the measure of angle B plus the measure of angle CBE, and explain how you know. In our previous example, we learned that adding those three angles together was 180 degrees by straight angle theorem. We're going to use our answer to explain why ABC is equal to there. So let's just use the converse of what we did before. When we take this triangle or these angles here, what we'll need to be doing with these is we want to use the same principles that we used a couple lessons ago, alternate interior angles. We see the rotation around the midpoint will show us that these angles, angle C, is equal to angle EBC. So we're going to just focus on one side at a time. We're going to look at this angle right here, and we're going to see that under a rotation of 180 degrees around a midpoint, we'll map angle C to angle EBC. So our proof or our evidence when we're talking about this measurement of this angle up above is a rotation of 180 degrees around the midpoint of segment BC. Thinking about that same principle, but on the other side of the triangle, we can use the exact same logic to define the alternate interior angle of angle A to angle DBA to make sure that we understand that the angle measure here is equal to the angle measure here. Let's go ahead and get rid of some of this other work. And we'll go ahead and do the same thing, do a rotation of 180 degrees around the midpoint here in the middle. And we will see that this angle here in the triangle maps directly with angle DBA. We'll also see the angle DBA maps directly with the angle measure of A. And again, a rotation of 180 degrees switches A and B. And we see that regardless of the way that we have our drawing, that these two angles map each other directly and exactly. Why will this work every single time? Or explain why your argument will work every single time for every single triangle, meaning explain why the sum of any angle measures in any triangle is 180 degrees. Well, as we do this, our explanation comes back to the same principles that we've been using throughout this entire unit, and that's that rigid transformation preserves angle measures. When we look at these angle measures and we take the bottom piece or the bottom part, let's take into consideration the bottom part of this diagram is a straight line. That means that if I look at any point on here such as C, and I look to the left and I look to the right, this would be a straight angle. Likewise, if I look to point A, it would be a straight angle. The same thing would happen if I found the midpoint of segment AC. I could see that this becomes a straight angle across the bottom. I can see the same relationship here as I look at line DE, where point B is not in the midpoint of this line, but we know that as we go from one point on the line and travel and around all three of these angles, that we see the same relationship of 180 degrees. When we rotate this angle that was given, angle A, or the measure of angle A, when we rotate 180 degrees around the midpoint of its related line, or of one of its related sides, we can see the relationship that this angle right here is an alternate interior angle to the original one, and that alternate interior angle is of parallel lines. Therefore, these two angles must be equal to each other. The same relationship exists when we take a look at angle C, or the measure of angle C, when we compare it to the measure of angle EBC. So what we can see is this, and what we can see is our rationale, just like with everything else that we've done in this unit, is that basic rigid transformations preserve angle measures, and they can be used to prove that the interior angle sum, angle A plus angle B plus angle C, are equal to 180 degrees because they relate directly to the same drawing as a straight angle. Remember this picture? Let's look at the same type of thing that happens underneath a rotation. This one says the diagram of BDFH that has been made by images of the triangle ABC under rigid transformation. In that video, we learned that we could take a rotation of 180 degrees around the center point in this figure to map triangle ABC to any one of these triangles by a rotation of 90 degrees clockwise, 180 degrees, and 270 degrees clockwise, or the other way around. They're telling us here the angle BAC is 53 degrees. If that is the case, it says find as many other measures as you can. Well, let's look at these pieces. We know inside of here this is a square. That means that this angle right here would be 90 degrees. And then we know that the consequence of rotating from one straight line to another is a 180 degree rotation. So that leaves us with the values here of 180 and 153, or excuse me, 180 and 53, and then we have to just find out what's missing. Oh my goodness, I got that wrong, 90 and 53. So we know that 90 plus 53 plus the unknown has to equal 180 degrees. 90 and 53 is 143 degrees. So the remaining balance of that will have to be 37 degrees, would be equal to x. Knowing that these three angles here on this straight angle will be used under a rotation, we can see that each of these other intersections here will have the same principles and the same properties because of rigid transformation. Let's go ahead and find our center point, or center of rotation here, by taking corresponding points on the figures. And then we'll take that center point and make that our center of rotation. And then we'll be able to visually confirm that the angles on this side of the figure that show the angle measure of the smallest angle on the triangle, the next larger angle of the triangle, and the 90 degree angle of the triangle are all equal to each other as we rotate from one intersection to the next. This being 37 degrees, 90 degrees, and 53 degrees. Go ahead and rotate 90 degrees again. We see the same relationship again. 37 degrees, 90 degrees, 53 degrees, and one final time we see the relationship again. Again, our reason comes down to simply that rotation is a rigid transformation, and all rigid transformations preserve angle measures and they preserve lengths of segments. What we can conclude is that all of these angle measures here are congruent to the angles that we measured earlier by the virtue of those rigid transformations. If that weren't so, then this picture would not be as it sits. That is the end of our lesson. What I want you to do is take a lot of time to actually read through this entire summary. The big thing that we have to understand with this is that using parallel lines and rotations allows us to understand why the angles in a triangle always add up to 180 degrees. A 180 degree rotation of triangle ABC around midpoint B, if we're going to make this a midpoint, or around a midpoint of AB, excuse me. Around this point, we'll exchange some information. It will exchange this angle for its alternate interior angle. And because we're dealing with alternate interior angles of parallel lines, these angles must be equal to each other. We can understand that a rotation of 180 degrees around the midpoint of segment BC would offer the exact same relationship where angle Z, which is given in the triangle, and its related alternate interior angle based off of this transversal will also be equal to each other. We also know the angle DBE is a straight angle. Therefore, the added measures of these three angles, which are the same measures as what we find in a triangle, add up to 180 degrees. We have proven that all triangles, no matter what their size, will always have a sum of their interior angles as 180 degrees. Thanks for following along today. We'll practice these same principles in our homework today. If you have any questions, please make sure to give me an email, send me a message of some kind, let me know how I can be of help. Thanks for hanging in there. This is the end of Unit 1. We'll be preparing for Unit 1 test. Make sure that you don't give up. Make sure that you reach out for help. Have a great day.